Moving on with the thermochemistry, we're going to look at standard enthalpy of formation. That sounds like a blast, right? You might recall standard enthalpy of formation from first year chem. I know I usually do a little bit of this with my first year folks, and I'm hoping that maybe you did too. Standard enthalpy of formation is just the energy change or the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements, with all of those elements being in their standard state. Interesting. Okay, well that makes some sense. Enthalpy of formation. We're looking at the energy change that accompanies the formation of a particular compound. When you look up these values on a chart, which you'll usually do, like if you're doing the homework, I think you got to get them from the appendix of the textbook. They're going to be usually in units of kilojoules per mole. The symbol will look kind of like this. Delta HF, heat of formation. And sometimes people are a little confused by that degree symbol. That degree symbol just means that the elements were in their standard state. So for example, if I was looking at the, enthalpy of formation of copper oxide, the copper was a solid and the oxygen was a gas. The elements were in their standard state of matter. That's all the little degree symbol means. Now, that reminds me, what if you were looking up the enthalpy of formation for a particular element? For a particular element, the standard enthalpy of formation is 0. For example, something like copper in the solid phase, elemental copper is naturally occurring. There is no energy change that accompanies the formation of solid copper. And we're not talking like nuclear reactions or anything funky here. The elements on the periodic table are naturally occurring. Most of them. Don't think too hard about this. Yes, there are some synthetic elements, but no, you're probably not going to be dealing with those. It says as long as you're using like copper in the solid phase, if you look it up on the chart, its enthalpy of formation is probably 0. It occurs naturally. Same thing with like O2 diatomic oxygen in the gas phase. That's its natural state. Its enthalpy of formation value will be 0. Now you can have like molten copper. Oh, this is going to be cool. We're going to do a reaction in the lab where we will make molten iron. That is darn cool. Well, there's definitely an energy change in the production of molten liquid iron. That's not its normal state. Well, then you might find an enthalpy of formation value. Or like I can have liquid oxygen. But again, then that's going to be highly exothermic. You have to release a ton of energy from the gas to get it down into the liquid phase. There would be an energy change associated with the change from a gas to a liquid. Then you would find a number on the chart. But for the most part, we're going to deal with the elements in their natural state of matter, their standard state. We can use these heat of formation values then to calculate the energy change from a chemical reaction. This equation's in your book. It's also in the packet, and it looks exactly the same. And this is what you may have done last year. We can go the summation, the total enthalpy of formation for all the products, minus the total enthalpy of formation for all the reactants, and we can get the energy change for a chemical reaction. Products minus reactants. Well, let's do it, shall we? Okay, so again, this is what I'm thinking maybe you did last year. We've got this balanced equation. We are burning some ammonia in the presence of oxygen. Oxygen gas, O2, diatomic oxygen gas. We're forming nitrogen dioxide and water. So like on the AP test, you're not going to have to look these up like in the back of a textbook. You might for the homework. They'll give you these enthalpy of formation values right in the problem. Notice, however, that they do not give you oxygen. because they're going to expect you to know that O2, diatomic oxygen in the gas phase, is how it occurs in nature, and its enthalpy of formation value is 0. So again, they probably won't give you the naturally occurring elements. They'll expect you to know it's 0. Okay, so let's get these going. Delta H, they're super easy. You just have to stay kind of organized. Delta H is products minus reactants. Total energy of those products. Notice that if I check the nitrogen dioxide on this chart, it's 34 kilojoules per mole. On the balanced equation, I am forming 4 moles. So all we have to do is multiply by the coefficient in the balanced equation. People will forget to do that. So I need to take 4 times the heat of formation value of that nitrogen dioxide, 34.0. Okay, so common mistake number 1 is that they forget to multiply by the coefficient in the balanced equation. Common mistake number 2, this is products minus reactants, and they want to start with the reactants. So this guy here, and I'll leave the kilojoules out, it will be in kilojoules. This is for the NO2, the nitrogen dioxide. To that, I'm going to add the total energy of those 6 waters in the liquid phase. Negative 286.0. Okay, so that was water in the liquid phase. Note too, like if you're doing these in the homework, just be a little careful because that chart in the back of the book is going to give you water in the liquid phase and the gas phase. So just check the balanced equation. Often, like after a true combustion, the water is in the gas phase. We are burning the ammonia, but we must not be releasing quite as much energy because that liquid water is formed. Okay, so I have products. Now I need to subtract my reactants. I'm going to have 4 ammonia, negative 46.0. That's my ammonia. And I have, I'll put it in here so it doesn't screw you up. 7 times nothing. That's the oxygen. It's not in the chart, but the heat of formation for O2 diatomic oxygen gas would be 0. Okay, so there's the setup. So again, common mistakes, it's products minus reactants. Common mistake, look at the coefficient in the balanced equation. And then again, sometimes people have this set up right, and they're just kind of knuckleheads when they plug it in their calculator. Like they miss minus a negative or something kind of crazy. So I usually just simplify these 2 groups. So if I plug this in my calculator, 4 times 34 plus 6 times negative 286. Okay, so this grouping here is negative 1,580 minus, and this will just be 4 times negative 46, negative 184. So yeah, they'll just kind of miss that it's minus negative. Like they'll have it all set up right. This delta H is still exothermic, negative 1,396 kilojoules. There it is. Using enthalpy of formation values to calculate the energy change of a chemical reaction. Super easy, right? And again, maybe something that you've done before. That would be kind of handy. Okay, let's try another one. This is the one that we're going to totally do in the lab. But we're going to make this a little more exciting than the way they've got it listed here. We're going to take some aluminum, solid aluminum. We're going to react it with some iron oxide, which is just rust. It'll be like a rusty colored solid. It's kind of a single replacement. We can form aluminum oxide and iron. But depending on how much energy we can make this thing release, I can get that iron to form not in the solid phase, but molten as a liquid. We're going to use like really, really fine solid aluminum, like super tiny particles. And kind of the same with the iron oxide. It's really a fine powder. We'll need to add a little energy to get it started, but I think I can get this thing to release enough energy that the iron would become molten. How cool. Okay, so even if I look at the reaction as given, products minus reactants, this one's super easy. Delta H. Products. I have that aluminum oxide. There's just 1 mole. Aluminum oxide. Negative 1,676 kilojoules. Okay, so there's my aluminum oxide. They do not give me the iron in the chart. But that's because iron in the solid phase, that's its standard state. So that's going to be plus 0 for the iron, for the 2 iron. I don't care that there's 2. 2 times 0 is 0 last time I checked. You would not need to put that in there if you're showing your work. I'll just put it in there so you see why I'm not including the iron. It's 0. Products minus reactants. There are 2 aluminum. Aluminum is naturally a solid, so it's going to be 0 for the 2 aluminum. And then we add the total energy for that iron oxide. Negative 826 for the Fe2O3. Cool. Okay, you don't have to put in the zeros. If you know that those pure elements are in their standard state, their enthalpy of formation value is 0, they're naturally occurring, you can leave those out when you show your work. And then you just plug this in your calculator. Negative 1,676 minus negative 826. Again, that's something that sometimes people will miss. So this is still exothermic. Negative 850 kilojoules. Gosh, that's so easy, isn't it? And I think we can do this one in the lab and get a little more energy released, even a little bit more than that, to the point where this iron will be liquid. It's going to be nuts. Okay, so again, if you feel comfortable with this, excellent. In the next video, we're going to kind of do a blast from the past and compare this method of calculating the energy change for a chemical reaction to what you did back in Chapter 8. Do you remember bonds broken minus bonds formed? Oh my gosh, again, we're reviewing for the AP test and we're not even trying to. But all of a sudden you know so much information that we can kind of like go back and tap into some of these old topics and see how they're related. It's going to be so awesome. I can't wait.